first of all, on behalf of the Indian Academy of Sciences and the Academy Trust, I welcome you all to this very special event to celebrate the National Science Day through a lecture by Professor Pradeep. And the National Science Day, all of you know, is on February 28th in India, and it marks the discovery of Raman effect as announced by Sir C.V. Raman, for which he had received the Nobel Prize in Physics in 1930. And this day is celebrated here to spread a message about importance of science used in our daily life of people and also welfare of human beings. The theme of the National Science Day this year is an integrated approach in science and technology for sustainable future. And all of you know Pradeep is absolutely brilliantly suitable for this type of a theme, for a lot of interesting work that he has done in the recent years. So Professor Pradeep is the Institute Professor, also Deepak Parekh, Institute Chair Professor at Department of Chemistry in Indian Institute of Technology Madras. Professor Pradeep conceptualized and built the International Center for Clean Water, a new initiative at IIT Madras. His education, he earned a PhD degree in chemical physics, working with Professor C.N.R. Rao and Professor M.S. Hegde at the Indian Institute of Science. Subsequently, he spent about 2 years as a postdoctoral fellow at the University of California, Berkeley, and Purdue University, Indiana, before joining IIT Madras. He is a recipient of many accolades and honors, and it's difficult to go through all of them. To name a few, he is a recipient of Shanti Swarup Bhatnagar Prize in Chemical Sciences, Twas Prize in Chemistry, Padma Shri, Nikki Asia Prize, and he's a fellow of all the Science and Engineering Academies of India, Royal Society of Chemistry, the Academy of the Developing World, and American Advanced Set of Sciences. He's a J.C. Bose National Fellow of ACRB and DST. Professor Pradeep's work is broadly in the area of molecular materials and surfaces, and he has made monumental contributions in this area of chemistry and science. He's developed lots of technologies, and particularly the clean water technology he developed is estimated to have reached about 9 million people. His group developed several other technologies, and many companies globally are interested in expanding this further into translation and real-world applications. It's my pleasure to have Professor Pradeep and invite him to deliver his National Science Day lecture today on science, technology, and innovation for sustainable clean water. Over to you, Professor.
Umesh, it is always a pleasure to talk when you invite, and it is also a great pleasure to be with all of you on this very important day. All of us practice science, and I know that science flows through your veins. And in that process, we celebrate various disciplines. And we practice those disciplines, and we don't know anything else. We identify ourselves with those disciplines. So it's always a pleasure to talk to such people about one's own work. And I chose to talk about this title that you see. I should also thank Hesh Chandra for this opportunity to talk to you. Water, as all of us know, is a triatomic molecule. But the complexity of this molecule is probably not understood adequately. And therefore, there are more papers coming every year on water, on fundamental issues. We will touch upon some of them as well in the course of this lecture. But although I will not be looking at water as a molecule today, although we study this aspect as well in the laboratory. Our science is, the many of the things that I'm going to talk to you are going to be technology and the pointers to future. What these technologies offer us and how they look in the foreseeable future, maybe 2030 and beyond. The most important point that all of us must realize is that water is our most important inheritance. This is probably evident from pictures of this kind. This picture is called the Earthrise. This picture was taken on December 24th, 1968, by the Apollo 8 astronaut, William Andrews. And this is said to be the most influential environmental photograph ever taken. As the moon is rising, and as you are seeing the Earth rising with moon in the background, this picture was taken. And you see this fantastic place, which is filled with water. And that place, if we can mute these this sound, that will be useful, because it is sort of disrupting some other noise, wherever it's coming from. So this kind of pictures are many, and most important of these is this picture, the pale blue dot picture. As Voyager 1 was just passing the solar, going away from the solar system, passing Uranus, it took a last picture, looked at the solar system, which it was leaving, and took a last picture. And that picture, in that picture, you see this dot, the pale blue dot. That blue is nothing but water. And therefore, it is quite obvious that water is the most important inheritance of our planet. And today we know that not much of water comes from outside, and all the water is essentially inside the planet. And it is a fixed number, something like 33 into 10 to the power 45 molecules of water. And although people have written about this, that water could be coming also from other planets. Most importantly, in this book by Arrhenius in 1908, he talked about the possibility of life coming from outside. Along with it, of course, water too. But today we know that the exchange of materials from Earth to outside is pretty small. Water, therefore, is within us, and we have to solve all our problems with that water inside. It's important also to understand that water is the simplest and simultaneously the most complex problem of humanity. There is a water cost in everything, including this water, this lecture that I'm giving. And our economic, social, and cultural outcomes, everything can be traced to water. Where there is water, there is richness, and where there is scarcity, it is the region is poor. And when there is water, there is food, etc. There are very interesting correlations about water and the rest of various aspects of civilization. Water is also this issue of contradictions. On the one side, there is drought, on the other side, there are floods. When you look at the world today has witnessed a whole lot of benefits. We have rapid transportation. We have high-speed internet. We have power. But we realized all of these with advanced materials. But these advanced materials have also provided a lot of disparities in water. And this is why we need to talk about new advanced materials, which will probably provide water for all. And in that context, we need to understand that our dreams became reality with materials. or dreams of transportation, or dreams of energy, or all of these became reality with materials. I took this picture to illustrate this point, that when Jules Verne wrote this great book in 1865 about going from Earth to Moon with a rocket, he talked about the material used for the rocket. The material that was suggested in 1865 was aluminum, although aluminum was discovered only in 1825, and the first little bit of aluminum was produced only in 1858. He talked about use of aluminum, which started its commercial production in 1889. And with aluminum, of course, he talked about sending man to moon. They could not reach there. It started orbiting moon, etc. is the story of this particular novel. But looking back, looking at the problem of water, maybe we should be solving this problem with materials. So look at these numbers. 1 kilowatt of solar panels today costs about 35 to 45,000 rupees. A 150 ampere hour rechargeable battery to charge whatever power that is coming from this solar cell is about 18,500 rupees. And seawater desalination today for a cubic meter, 1,000 liters of water is 2.4 kilowatt hour, or 2.4 units, or about 40 to 50 rupees, with embedded subsidies, which are not counted. Now, with today's proposal for green hydrogen, maybe it is possible that seawater desalination with hydrogen energy could make water possible, water really cheap by 2030. Look at numbers. Hydrogen and oxygen making water is about 286,000 joules per mole of hydrogen. So 1 kg of solar hydrogen today is at 600 rupees, they say. I have not seen really, but these are the numbers. And it could become 150 soon by whatever, 2030. This can make about 143 million joules of energy. Desalination, as I said just previously, used 2.4 kilowatt hour, or about this much of joules per cubic meter. So 1 kg of hydrogen can therefore make about 16.56 cubic meters of water, or that will translate to about 9.06 rupees per cubic meter, or 0.9 paisa per liter. Obviously, all that thermal energy is not going to be electrical energy, and all that electrical energy alone is not enough for desalination. All of these issues are there, but it is very much feasible, possible, that with the technologies available, solar desalination would make water plenty of water. Now, having sort of given that kind of a forecast of 2030, what is the reality today? The water cycle has been net zero for a long time. We got enough water from the rain, and we recycled it, that hydrological cycle. But we have opened that cycle in the course of civilization. Water has been circular. Essentially, water plus carbon dioxide gave sugar plus oxygen. And that is what this world is about. And we, as animals and human beings, took this sugar and oxygen back to water and carbon dioxide. And in that process, we live. And for our living, we require just about 29 billion tons of CO2 per year. And we are making 258 billion because we have opened the cycle. And we are burning far more sugar products, not really sugar, but petroleum and several others. It's not that we are only making sugar, we are making carbohydrate, we are making terpenes and many others, alkaloids and many others in that process. But we burn many others, and we produce many others, not only water and carbon dioxide, we produce nitric oxide and nitrous oxide and many others. The point is also that we opened a water cycle as well. So in this process, to make a lot more CO2, we are also producing a lot more water, which was sort of embedded in these fuels. You won't see water in petroleum, but petroleum itself came from carbohydrates and cellulose, which it's embedded water. So if you are addressing this issue of closing that water cycle, we are addressing many other related issues as well. So while all of this is going on, water itself is exciting from many other perspectives. I took two examples from last year, 2021 literature, showing elastic ice. And 2021 also gave a very interesting paper on metallicity on the surface of water and showing plasmonic behavior and things of this kind. So water therefore continues to excite a lot more people. But that molecular water and that droplets of water apart, water in the big capital W is also exciting. All of these numbers are by and large known to you. We have so much of fresh water. We get a lot of water in the form of rain, and our average rainfall is not very bad, although it is 85th in a list of 186 countries. We are far better than many other countries, such as Egypt, which get very little water. So water is big, but water has given us very many big gaps. At the same time, opportunities, wealth, and you will see how how big that water business is very soon. And therefore, there can also be great satisfaction, intellectual, material, and societal. Look at this picture. It's about water withdrawals. Water withdrawals, of course, suggest that technology, those who have technology would withdraw more water. And that is true. And they consume far more water. But the next figure will surprise you. When they start withdrawing water, there is no water risk at all in those countries which are withdrawing a whole lot of water, but they have plenty of water. Those who don't withdraw enough water, they are at risk of water, and the water risk is centralized in regions where there is no water and where they don't use enough water. And so this also tells you that a whole lot of technologies which are used, which are water intensive technologies, which make water utilization high in those countries, they don't get depleted in water just because nature has given them water. In other regions, nature doesn't have, has not given enough water. The natural resources are limited. And if you want to have life similar to that of a developing nation, completely different technologies are needed as the kind of thing that I just talked about. That water, that thought of universal water, that thought of the universal conservation of water would also tell you that water has to be considered from another perspective, from a water footprint perspective. Water footprint is considering both production and consumption of any product. And production and consumption becoming, well, production is becoming global, consumption is local. You see that a lot of water is coming from other countries. A lot of water is going out from your country to other countries. So if you look at all of these, for an equitable distribution, one has to look at a global water footprint, which is acceptable for the world. And that would limit the kind of technologies that one can use for the world. That would also limit the kind of products that can be distributed across the world, the kind of technologies that we could develop for future. In that context, we must also understand another important thing. How big is this water business? One study says that total water infrastructure value for a connected global population of 9 billion by 2050 would amount to that much. That study, well, was taken forward, and it was shown that only about 36% of the African population and 44% of Asian population will be connected to a sewer network by 2050. So if you were to say that life comparable to that of a developed nation, if that requires a connected water network, it is quite unlikely that we are going to accomplish that in the foreseeable future. In order to look at these numbers, you should also look at the global wealth. The global wealth, well, for India, the total wealth is somewhere around $13 trillion. And that of America is about $130 trillion. So that means half of this American money, wealth that you're talking about, is really required for a global connected water network. This is where water is coming into the biggest, well, the bigger picture. Water is there in every aspect of our planning. Water is there in poverty, water is there in hunger, water is there in good health, water is there in quality education, water is there in gender equality. Therefore, that wealth that I just talked about is also highly connected to several aspects of development. And that is where the sustainable development goals look at water in each one of them in significant detail. So having said all this, we also are aware that India's water challenges are plenty. But we must give enough credit to what is going on today with the Jal Jeevan Mission, providing functional household tap connection. And that is nearly 100% in Telangana and 100% in Puducherry, etc. It is rapidly expanding. And towards the end of this talk, I will come to this. We are doing extremely well in areas such as this. However, a lot more is needed. When I say a lot more is needed, look at this water-rich country with so much of water that is coming in, but 50% of our microbial diversity is lost in many of our rivers. Globally, it was estimated that 83% of the freshwater species have declined, not lost completely, declined in the past 50 years. In India, there is no river which is not contaminated. We monitor one river in Tamil Nadu, and we find that the microbial diversity is rapidly declining. And this is a scene that is there everywhere in the country. And there is plenty of groundwater depletion. And if you look at just a few years of 2002 to 2008, this is what is happening. 67% of Indian agriculture in several regions is being fed by groundwater. So if all of these is taken together, one would ask this question that if groundwater is depleting so fast, and if there is not enough water to suck from the earth, how will you increase our GDP? This is where I take this picture from Peter Gleick, who introduced this concept of peak water. And without getting into a lot of details of this, America kept this freshwater withdrawals at these 1974 levels and maintained it till now. While maintaining this, you see that American GDP is going up. This means that completely new technologies are needed for recycling, for production, Although some of these you may attribute to production moving to Eastern countries, but it's important to realize that very new technologies have come in water conservation. If this were to happen, India will also increase its GDP and completely new technologies will come in this area. We get enough water. As I said previously, we get plenty of rainwater. If we were to conserve this water and utilize it, we have enough water. We use just about 8% of our fresh water that is coming in. Rainwater harvesting is just about 8% in our country. And if that has to increase, or that can increase, India will change its landscape. India continues to get water, and several regions continue to get the same amount of water. In the past few years, in fact, we have increased water in Chennai, about 1400 millimeters of rain. Across the country, this is the scenario. However, we are not managing our water well. So we see that there are plenty of issues around water, but all of these issues cannot be solved just by technology. A lot more policy initiatives are needed. A lot more technologies are also needed. Because we have kept the technologies the way they are, they keep contaminating water. Advanced technologies are needed to ensure clean water. This is where we have done some amount of work. A lot of technologies have come, and we have utilized towards the last few years, the last tens of years, we developed several nanomaterials and introduced them into the market. I've been saying that affordable clean water is actually a problem of advanced materials. Advanced materials, I mean several nanostructured materials. We have created several new adsorbents, new sensors, new catalysts, new phenomena, new devices, and all that subject matter together is called aquananotechnology. What has really happened in nanomaterial science is that the materials have become atomically precise. So today, a particle such as this is atomically precise. 25 atoms of gold, 18 ligands, and with 1- charge state, you get a mass spectrum of this. In fact, a high resolution mass spectrum, 7390.5718, and that tells you that it is possible to do chemistry precisely and understand that chemistry with such molecular systems. And although these are not the materials to be used in the field, using these we can understand chemistry. So what we have done is we looked at the chemistry of contaminants in water or nanomaterials. And we found that arsenite and arsenate could absorb, arsenite and arsenate absorb on several nanostructured materials in a highly efficient fashion. And using such materials, we could develop filters without using any extra energy. And they give you US EPA or WHO quality water with no additional environmental implication. Look at this picture. This is a pump, a 40-year-old cast iron pump in Nadia district in West Bengal. This boy is pumping this water from a depth of about 80 feet. And water that comes out, one stroke of this boy gives you about 300 ml of water. That water has some amount of iron. And this platform is stained with red iron oxide. And in this region, we know if there is iron that is present, with the red stain that is present, there can be some arsenic. And you measure this arsenic concentration, it is about 60 parts per billion, 6 times higher than the limit. Next, maybe about 100 meters away, you may have another location where the arsenic concentration may be about 100 parts per billion or 200 parts per billion. So this is the situation here. And this problem has been there for the past 60 years, we know, in India. And globally, it is about 108-year-old problem since we started measuring that. So we know that this problem exists, but then solution has not been there because affordable materials have not been there. So when advanced materials of this kind were there, we could put them in the form of a filter. In fact, this arsenic material is just very small in this thing. Rest of the materials are essentially to remove particulates and such other things. You get 1,000 liters of water every day. And you can run this filter for 2-3 years without changing materials, without changing active media. And even after removal of this active media, which is sort of saturated with arsenic, it can go back to the field because these materials won't release arsenic at a very large concentration. So it will release arsenic at the background concentration present in the soil. So therefore, there is no environmental toxicity as a result of this. The cost of producing this material is such that we can provide 1 liter of water with about 2 paisa. 2 paisa will be the cost of materials and operational expenditure that is there. We will come to that in a minute. So it means that there is a very effective technology. The basis of this is this kind of materials we call biopolymer reinforced nanostructured materials. We introduced in this paper a very important concept called water positive materials. So in the past several years, we have had a number of materials, but in the course of for water purification, in the course of producing these materials, we contaminate water. In the course of their useful life, of course, we create clean water. After their useful life, they go back to field and then again recontaminate water. So you ask this question, what is the net water outcome from these materials? Oftentimes they are not very high. So this is where we introduce this kind of materials. 1 liter of water used for its production give you about 500 to 1,000 liters of water, 100 or 1,000 times water positive materials. And these materials don't cost additional carbon footprint, and there is no energy requirement because the entire process is made at room temperature. So the idea is creating porous materials with the kind of selective chemistry so that water can be filtered and contaminants can be removed. So think about this. So there are many biopolymers. One example is chitosan, another could be cellulose, and there are various kinds of banana silks and various kinds of silk and proteins available. Imagine on this biopolymer, you are crystallizing tiny sheets of aluminum oxyhydroxide. And this aluminum oxyhydroxide turned out that it is about 50 nanometers long and about 50 nanometers wide and 15 nanometers thin sheets. And if you deposit this well in a controlled fashion, you can create matchboxes, like the kind of thing that are shown here. It's a 2-dimensional projection. So these matchboxes have about 15 nanometers cavities in which nanoparticles could be put in. And these materials are all synthesized at room temperature by slow cooling or a slow precipitation. And you finally get a river sand-like material with Young's modulus comparable to river sand. So they are like seashells. You are synthesizing seashells at room temperature using soluble carbonate ions on calcium ions. And similar kind of process is what is used here. That gives the green nature of the material. So if you put material, let us say nanoparticles in it, what is the advantage? The advantage here is that you can select the nanoparticle that you want. You can put an antimicrobial material, or you can put an anti-arsenic scavenging material, or a mercury scavenging material. Many of these materials could be put into these cavities. Imagine silver is put into these cavities, it releases silver ions. But silver ions normally from silver nanoparticle, that concentration of silver ions will decrease in the course of time in real water. The reason is that silver present in silver coming out from the surface will be inhibited by the depositing calcium silicate from real water. Real water has silicates and calcium ions. They form a tiny layer of calcium silicate. Although I'm telling you this in two sentences, it took about 3 years for us to understand how thin is that calcium silicate, which stops this silver ion release. So in the laboratory, we study the silver ion release for thousands of liters of water, not 10 liters or 100 liters. So you also see in this single slide how our laboratory has become a place of industrial production and testing. So we run 10,000 liters of water testing. And that is impossible in a typical chemistry laboratory. So this drug-like release is what you get in such a material, and that kills bacteria from live to dead bacteria you see. Now you also ask this question, does it lead to nanotoxicity? It doesn't give you nanotoxicity because you are releasing only ions. You put nanoparticles, of course, nanoparticles are picked up by bacteria, and you see all of these particles, and you can collect the spectra from these particles. But in the case of ions, you do see lysis of bacteria, you see the destruction, but you don't see nanoparticles. So toxicity not being there, such materials can be used in many ways. The other kind of nanoparticles we use extensively in the field are iron oxyhydroxide. The kind of iron oxyhydroxide that we use is a metastable iron oxyhydroxide called 2-line ferrihydride. And that 2-line ferrihydride is almost amorphous. And you barely see some features in the XRD. In TEM, you don't see anything. But upon electron beam induced crystal growth, you see tiny crystallites. And this is to tell you that how small these particles are. But good thing about these particles is that they selectively absorb arsenite and arsenate ions, giving you specific features in the Raman spectra. This is where I connect to Raman spectra. And with this, you can model a nanoparticle. And with that, you understand what is the theoretical adsorption capacity. You modify specific crystallographic planes on the surface, and you create maximum adsorption capacity. You create such materials, and you put it into a small cartridge, and you pass water through this containing 100 parts per billion arsenite and 100 parts per billion arsenate, and you get less than 2 parts per billion arsenic-containing water in the output. And this 20 grams of this material can remove arsenic from about 1,200 liters of water. And that means that you can put it into commercial filters. A typical arsenic removal plant in West Bengal in Nadia district here, it produces about 20,000 liters of water per hour, or about 200,000 liters of water per day, 10-hour operation. And this whole thing uses huge tanks, as you can see. These filtration tanks are of this kind, but it can all be reduced to less than 6 inches of filtration towers with these materials. And the land area utilized is just 3 cents of land. And that is the capacity, as I said earlier. This is the capacity at which we are operating here, about the same. The concentration is that at the input level, and this is the concentration at the output level. Even after 8 years, the plant is running. So at that point in time, it was all fitted with plastic tubing and connections and all that. Today, it is all cast iron across the country. And these kinds of filters are there everywhere. And this is one picture of this month when the fields are all in full bloom in Punjab. And this is how a plant looks like. And the price of that is 2.1 paisa per liter with all the costs, including the operator costs, put into the calculation. And such sensors are now fitted with, such filters are fitted with sensors now. At the production level, at the consumption level, the entire data comes on the cloud. And here is a short movie, 1 minute, to show you what this is about. You may not get the sound, but nevertheless, the sound is only music, so you are not going to miss much. So we see that if there is water which is contaminated, there are a large number of nanotechnologies or materials with which the contamination can be removed affordably and sustainably. But if there is no water available, one approach would be to have atmospheric water harvesting. We use a tiny nano electrosprays. These are electrosprays coming out of 50 micrometer thin tubes. And these mist contain particles, and these particles can be used to grow nano brushes. And these brushes are very similar to the kind of fibers that you see on plants or thorns. And on them, you have condensation when the atmospheric temperature is below the dew point. And that is an everyday observation. So we have such surfaces on these metallic substrates, and water humidity is drawn to that surface. The surface itself is cooled with electrical power, and you get clean water. And that has resulted in a company. And today that company is making water filters, or this is not water filter, water generators from 35 liters per day to 2000 liters per day. Now, this is about active water harvesting. There are a number of passive harvesting structures utilizing nanomaterials, such as these metal organic frameworks. They pick up humidity in the night, and in the daytime, by absorbing sunlight, they release that humidity into an enclosure where the humidity goes higher and higher and water condenses. And that condensed water can be collected and the cycle repeats. The whole problem, however, is to create efficient materials which do not leach into the water that is collected. This work is happening. There are several efforts globally in this regard. In India, there are several places where there is significant seawater intrusion, and that makes water saline, and there is a lot of brackish water as well. One way materials can help there is by a technology called capacitive deionization, a 40-year-old technology, but it has not been practiced commercially because there is no effective material. So we developed several advanced materials so that on these electrodes, we have electro-adsorbing materials with high capacity, and using that, oppositely charged ions can be collected on these electrodes. When the electrode saturates, potential can be reversed. The ions come into water, which becomes a reject stream. So by running this reject stream and production stream continuously, by appropriate cycling mechanisms, you create a clean water with about 18% reject, energy cost being substantially lower. This has also become a company today And we implement this across, especially in the coastal areas where there is significant intrusion, seawater intrusion, as I talked about. Also, there is a possibility of solar harvesting. So we run this on PV and photovoltaics. And these are such units being implemented in different parts of Karnataka, Tamil Nadu, Andhra Pradesh, places like that. So while this is happening, there are several new developments in the group, although they are not yet technologies. These are ways by which you create holes in nanosheets of molybdenum sulfide. And you look at these sheets in greater detail, they are molybdenum-rich sheets. When the sheets are molybdenum-rich, in presence of white light, from water, you can produce hydrogen peroxide. And that can destroy bacteria, that can destroy viruses. And it is possible to create such a filter module. You pass water, you expose this material with white light, and you see that bacterial concentration comes to zero by repeated passes. Now, you see that such materials have a lot of promise in rural water desalination. The canvas I presented to you shows that from materials to prototypes to implementation, it is possible to take water forward in a very big way. In that process, we also produce a lot of water data, and you will soon see how that data are going to help our country. Along with this, we work in other areas of water, which I sort of leave for the time being. In order to implement such technology, sensors are needed. Water technologies have created a number of handheld, cell phone-enabled sensors for a whole range of contaminants, including the entire periodic table. But what is happening tomorrow is that such sensors are becoming extremely small. As all of us know, spectroscopy is of this kind today. But in the foreseeable future, that spectroscopy is going to be integrated in the mobile phone. And it is happening right now because the spectrometers, the effective component or active component here can be as small as this, about 4 millimeters in thickness. Today, people are working on to reduce this to 2 millimeters. If so, this can go into an Apple phone. That means by shooting a picture or measuring spectra continuously and comparing that with a database accessible through cloud, you can get water quality. And we do this today in the laboratory. Although it is not as small as this, it is possible in the laboratory. Where is the data going to? As of today, with the Jal Jeevan mission, we are monitoring water quality across the country. These are select locations. These data are not available to the public as of now. But look at this particular data point, which is a cluster of locations. We monitor about 13 locations in this place. And those are those locations. And those locations are monitored by one of our startups. You see all of these water quality, pH, residual chlorine, nitrate, etc. In addition to providing water using the kind of technologies that I just talked about. This whole thing is going to give us a completely new kind of information of hydroinformatics, relating water quality with health and economics of the region, connecting to big data. Water, of course, is going to provide big data because every water point is going to be monitored every minute or every day. And that from so many people, you can imagine what this is going to give you. And that is also taking us to a digital twin of water infrastructure in the country. But all of these, if one has to ensure that that water and exciting opportunities, if they have to reach people, appropriate policies have to be implemented. In Chennai, when I sit here in Chennai, in Coimbatore, I see that arsenic contaminated water is coming into the wells. The reason being phosphorus or phosphate fertilizers, indiscriminate use of fertilizers in the soil, and the kind of fertilizers coming into the Indian market they are all contaminated with things such as arsenate and arsenite. As a result, arsenic has come to Tamil Nadu, although there is no geological reason for it to be there. And its impact is being felt, and hydroinformatics is going to reveal this. What is its impact across the country? While this is happening, we also have to ask, how can we eliminate this? See, a huge water footprint that we are going to create is also because of our agricultural practices. I talked about drinking water, which is just about 10%. About 70% of the water use is agriculture. That agriculture is because water guzzling agriculture is because of our agricultural policies. We produce a whole lot of cotton, only white cotton, disregarding all the kinds of cotton we had in our country, the red cotton, the yellow cotton, and the green cotton, and the blue cotton. They all went away because only white cotton could be dyed properly. In the process of dyeing, we, of course, contaminated our rivers, and the rivers became colored. Now, we also changed, well, there are several other practices that we have, including water guzzling agriculture. Rice is one of those crops that we have. But there are several native Indian rice varieties where that much rice is not used, that much water is not needed. India had about 100,000 rice varieties at the time of independence. We have just about 7,000 rice varieties today, and only a few hundred rice varieties are really practiced well. Even among them, there are water efficient varieties. And there is a need to promote all of these to ensure water security. So water science needs several new innovations. Why are we solving this problem, or why are we cleaning this water after contaminating it? Why can't contamination be removed? Why can't we practice sustainable chemistry? There are several examples globally. Water in agriculture, energy, and construction, that is becoming increasingly important in our country. Our cement utilizes about 15% of fresh water. In cities, we are talking about. Water in materials, such as water in detergents, plastics, and antibiotics to be considered. And completely different kind of detergents have to be thought about. And this is happening globally, and many things are happening in India too. And water, as I just mentioned about data, this data can actually be coming from wearable sensors. And that will make every individual producing water quality and quantity data, and thereby causing what is called water intelligence. And all of this would mean that water is put on the central stage, which means completely different innovations would happen. Just as data can drive Bangalore, water data can also drive other parts of the country. So for clean water for India, we need to care for our future with several planning that is sort of embedded in my talk here. Learn from the past, and we cannot forget our knowledge of the past in rainwater harvesting or conservation. Education, water has to become part of our educational practices. Water has to become part of action. Water has to become new initiatives. And there is a water cost in every product and service. And just as I talked about detergent, if we introduce a national detergent policy, which is very much lacking, there is an embedded water cost going to get into the detergents. That would make new detergents possible. That would make new innovations possible. That would make new treatment projects or possibilities or technologies possible. So in that process, which is taking water to net zero, there are several intermediate steps that one can do. For example, we look at water purification with RO today, why not RO versus CDI or capacity deionization? As I said, 60% water reject or 55% water reject versus 18% water reject. RO, why not we ensure RO with new filtration materials, pores like aquaporins? RO is not needed in many places. We require nanofiltration, less energy intensive. Absorption versus filtration, several 2D materials can come in. Wherever there is water doesn't require energy, we should look at zero energy processes like adsorption or atmospheric water harvesting. Atmospheric water generation is written here. And whenever you look at new materials, the amount of materials that are used in water purification industry is millions of tons in our country. And they need to go to the carbon zero. And they need to use room temperature synthesis methods. They need to use aqueous processes because 90% of the waste that is produced in typical synthesis is solvent waste. And that would mean that sustainability metrics have to get into water in a big way. So what I wanted to say was that towards that net zero future that I just envisioned, there are several in-between technologies, available technologies, and better implementation is needed. Of course, there is traditional wisdom that is important. There are friends of ours who introduce things like plant trees, 14 trees. If an individual plants, enough carbon will be absorbed, they say. And there are movements of this kind across. I'm closing my lecture by saying that it is possible to run this world with water. So that water can generate hydrogen with solar, and that hydrogen can create seawater desalination feasible, affordable, and environmentally sustainable. In that process, the excess energy that we may have can actually run our cities. So that would mean a completely net zero water cycle. And that would be the vision for future. Could be one of the visions of the future. With this objective, we have built this International Center for Clean Water at IIT Madras, at the IIT Madras Research Park. It is a 22,000 square feet research facility where anybody can come with an idea and go out with a technology, utilizing all of these resources. And this is, as I said, at the IIT Madras Research Park, a 1.2 million square feet research facility with over 170 companies housing it. My research is supported by or done by my students. Several of them are owners of companies today, supporting various supporting organizations, governments, and institutions who are behind us. Several of them you see here. And all of this became possible because of what we call the IIT Madras ecosystem. And that has made innovations possible, innovations thrive, innovations excel. And thank you very much for listening to the story. I'll be glad to take questions.
Thank you very much, Professor Pradeep, for a very thought-provoking talk with deep insights and connections with other aspects of life as well. So I invite questions from participants. Yes, Professor Chitra Mandal.
It's really, exciting talk, and I really like it. And especially when I see that so many entrepreneurship is coming into the market, and that is really very, very proud story of being an Indian. With respect to our state, we are really have a polluted arsenic very much, especially in a few districts. But now even in Kolkata, there are few areas where arsenic is a very big problem. So is any of your any of your students or who has, going around throughout India, are they coming to West Bengal or what? I don't know. I just would like to get your opinion regarding this.
Yes, we are there across, and in West Bengal there are about 1,400 installations in various districts. But Calcutta metropolis region is the arsenic affected water supply. There's still some water supplies. They are still following the Indian government norm of 50 parts per billion as the tolerable limit. And so the concentration is below that, and therefore it is arsenic filtration. Arsenic by such methods, removal by such methods is not practiced. Now, globally, it is known that arsenic, even at about 170 picograms, cause genetic deformation.
Yes.
So there are reasons to implement, but we continue to follow this guideline. But wherever there are new treatment plants being erected, technologies are being implemented. As you know, water technology enterprise is capital intensive. So when something is being put there, unless there is a big reason, there is no change that's going to happen. Now, one way that Kolkata can come out of this, I'm not talking about the whole of West Bengal, is to go to surface water. And your surface water is really clean, and there is no need of arsenic filtration in many parts. But there are many places where you need to live with, you need to have groundwater as the water source. That is where this problem is.
Thanks, Pradeep. Any other questions from the panel?
Yeah, Umesh.
Vijay?
Yes.
Yes, please, Vijay.
Yeah. Pradeep, thank you for a very inspirational talk. I know that you have an international center. What is the situation in places like Vietnam or Cambodia or some part of Africa where there is acute drinking water scarcity? And how affordable are we able to, let's say, deploy technological solutions in these areas? Any thoughts?
Thank you, Vijay, for asking that question. In fact, as we are talking about it, our people are implementing these technologies in Cambodia. But you will be very sorry to hear that the concentrations in Cambodia at select locations are far, far higher. Just today, as I was just talking to you a few minutes ago, I got the Cambodian water quality report. In some of the schools, they have 500 parts per billion arsenic.
My God.
It is so sickening and extremely sad. So these technologies are working, and NGOs are looking at the possibility of implementing this. Larger investment is required. This is where it is, but technologies are working, and people are. In fact, there are some of our. I got this one award from Japan, and because of that, somebody came forward and decided to implement these technologies elsewhere, and he has employed some people in different parts. It has started with Cambodia and in Africa, Uganda.
Thank you.
There's one question from participant Sajna Hamid. She is asking, what is actually elastic ice that you referred to in your talk, Pradeep?
Well, elastic ice is nanofibers of ice which were prepared by a particular kind of cooling process. They found that these needles are elastic when they are prepared under certain conditions. This is an ice form that really has not been structurally characterized.
Can we make arsenic free the whole India other than Punjab, sir? Is a question from Jaya.
Yes, madam. This is exactly what it is. And so I was telling that secretary that at least you say arsenic free Punjab is your mission. And she was in a position to accomplish that. So it's by and large, in fact, that mission is taken up by a number of people. All I wanted to say, Umesh, was that we have technologies available. We have shown the way. It is important that people take this forward and push in a big way, not necessarily just using this technology, but many other technologies. Why should people suffer at all?
Yes. Yes. Thank you.
Can I just ask one small
Yes,
question?
please.
How much the money wise? Suppose we wanted to plant such kind of one size plant in a rural area which is very much arsenic prone. How much money we had to raise? How much will be basic finance?
Typically, for a village, typical Indian villages are about 2,000 homes, 2,500 homes. The kind of a treatment plant with supply would cost somewhere less than about 18 to 22 lakhs.
Thank you. Thank you, Doctor.
Thank you. Yeah, thank you very much, Professor Pradeep, for presenting your brilliant science and also how greatly it is going to connect with the society, not just in India, but all over the world. We really appreciate your talk today. It's very suitable for the theme of National Science Day. And please, I request all of you to join me in thanking Professor Pradeep once again on behalf of the academic. Thank you, one and all.